Hello everybody and welcome back to HansenMath.com tutorial videos. Today's video regards finding the exact values of the zeros of cubic polynomials. So here you'll see in this area I have entered a polynomial equation. It's a third degree or cubic polynomial, x cubed plus x squared minus 53x minus 165. And I've chosen to use Desmos to graph this out, as you can see here. This shows the cubic nature of the graph. If we zoom in a little bit better, we can see the zeros, or the roots they're called. It's where the graph, the curve, crosses the x-axis. So we can see that it crosses at an x value of -5, an x value of approximately -4.083. Now I say approximate because that decimal goes on most likely forever, and that's just a approximation to the thousandth place. That's all Desmos will give you. And then over here on the positive side of the x-axis we have 8.083, and again that's just an approximation. So if your mission is to find the exact values of these zeros of the function, we have to dig a little bit deeper. So what I like to do is the following. I like to use Desmos to find the one real friendly, the nice zero or root that's an integer value, and that was the -5 right here. So I'm going to take the -5 and I'm going to put it in a little bracket. And then what we're going to do next is something called synthetic division. That's a way to knock this from a cubic down to a quadratic equation. And then from there, we can either factor or use the quadratic formula to find the remaining two zeros. So what we're going to do here is we're going to take this polynomial and we're only going to write down its coefficients. So the coefficient of x cubed is 1. The coefficient of x squared is 1. The coefficient of x is -53. And the constant that's remaining is a -165. Okay, so once I have those down, I draw what I call the answer line and the remainder line. Whatever goes in this corner will be the remainder. And we really don't want a remainder. We want this to work out clean. So the remainder should be 0. Okay, next steps here is to take this leading value, which is a 1, and bring that into the answer line. When you're in the answer line, you need to multiply back to the divisor, what you're dividing by. So 1 times -5 is -5, that goes there. And when you're in this column format, you just get a sum. So 1 take away 5 is -4. Now that I'm in the answer line, I multiply back. -4 times -5 is a +20. Now that I'm in this column form, I just get a sum, or I add. -53 plus 20 is -33. When I'm underneath the answer line, I multiply back. -33 times -5 is +165. These are opposite numbers, so I do indeed get a remainder of 0, which is what I wanted. So the usefulness of this is now we're no longer working with a cubic polynomial. We're down to a quadratic. These here are the coefficients. So we literally have 1x squared minus 4x minus 33. And what we can do now is we can use the quadratic formula to find the exact values of the remaining two zeros. The quadratic formula is x equals -b plus or minus radical b squared minus 4 times a times c all over 2a. All right, so if we use that and keep it moving here, we have x equals the opposite of b. Our b value here is this guy, so we have basically the negative of -4, which becomes positive, plus or minus radical b squared, so we have a negative 4 squared, minus 4 times, this is the a value, which is 1, times the c value, which is negative 33, all over 2 times a, which is 1. Okay, so now we have x equals positive 4 plus or minus the square root. Oh, let's see here. Negative 4 squared is 16. Negative 4 times 1 times negative 33 is 132. 132 and 16 is 148. So we have the square root of 148 all over 2. So now we'll do some simplifying. We have 4 plus or minus the square root of, let's see here. If we can find a perfect square number that goes into 148, we can break it down. So I'm going to guess that 148 is divisible by 16, and it is not. That gives me 9.25. Let's see, 148 divided by 4. Yeah, if I divide by 4, that leaves me with 37, which is prime. So I know that 4 is the biggest perfect square that divides into 148. I have my 2 on the bottom. So now I have 4 plus or minus the square root of 4 here is a whole 2. I bring over the square root of 37 divided by 2. And then finally now, since my whole 4, my whole 2, and this whole 2 are all divisible by 2, I'll simplify. This 2 here goes into 4 twice, plus or minus this 2 goes into that 2 once, and I have root 37. So if we take a look at this here, if you take a calculator and do 2 plus the square root of 37, you will get 8.08, which was that one. So that's 8.08, or exactly 2 plus root 37. And then this here should be the other guy. 2 minus root 37 is negative 4.08. Approximately, exactly, it is 2 minus root 37. So there you have it. We found all 3 of the zeros of the function. Negative 5 is one of them. 2 minus root 37 is the next. And 2 plus root 37 is the third, because the magic number here, you have to get as many roots as your degree, your highest power, which is 3. Next, we will look at one final example. This time, our function is negative x cubed minus 5x squared minus 8x minus 6. Take a look here. We have the cubic nature of the graph, but this time, using Desmos, you'll notice that the only place that we observe that this function crosses the x-axis is at negative 3. Okay, that's one real 0. It's real because you see it cross the x-axis. You can click on it, and that implies that 2 of the zeros must be imaginary, because again, we have to total to the degree here of 3. So if you only see 1 that's real, it's implied that the other 2 are imaginary, and you will not get those values off of Desmos. So we'll do it by hand, and we'll get to the bottom of it. So what we'll do is we'll take that real, nice, friendly 0 here of negative 3, and we'll put that in our little bracket. And now we'll write down the coefficients of the polynomial. So we've got a negative 1, a negative 5, a negative 8, and a negative 6. Lots of negatives today. Answer line, remainder line. Bring down the first coefficient here, which is a negative 1. When you are in this answer space down here, the only thing you may do is multiply back to the divisor. Negative 1 times negative 3 is positive 3. Now you add the columns. Negative 5 plus 3 is negative 2. Negative 2 times negative 3 is positive 6. negative 8 plus 6 is negative 2, and negative 2 times negative 3 is positive 6. Negative 6 plus 6 are opposite numbers, so we do indeed get our remainder of 0, which is what we wanted. So now, negative 1 here is our A of the quadratic, negative 2 is the B, and negative 2 is the C. So if we go x equals negative B, we're going to have that negative negative again. Now this doesn't always happen. That's just coincidence. That's two problems in a row. That will become positive. We'll do that in our next step. Plus or minus a big old square root of b squared, which is negative 2 squared, minus 4 times the a value, which is negative 1, times the c value, which is negative 2, all over 2 times a again being negative 1. Quadratic formula. So simplifying, we have x equals, the opposite of negative 2 is positive 2, plus or minus a big old square root. So let's see what we have here. Negative 2 squared is 4, and then we have negative 4 times negative 1 times negative 2, which is negative 8. So we have 4 minus 8 over 2 times negative 1 is negative 2. Simplifying this further, we have a 2 plus or minus the square root of 4 minus 8 is a negative 4. Now you can see where this is going here. This is why we're into the imaginary number system, because of the negative inside of the square root. And that's going to all be divided by negative 2. If we simplify a little bit more here, we have 2 plus or minus the square root of a negative 4. Well, the square root of 4 is 2, and the square root of the negative 1 part, because remember this is really negative 1 times 4, the square root of 4 is 2, and the square root of a negative 1 is the imaginary unit. All of that is divided by negative 2. So now, to get our solutions, we'll divide by negative 2. Negative 2 goes into 2 negative 1 times, plus or minus. Negative 2 goes into 2, really negative 1, but that's already accounted for here, so just 1i. So that is our solution. And since they're imaginary roots or zeros, you do not see them. So there's no way to really vet this on Desmos, because you do not see it cross the x-axis because it's in the imaginary number system. So in conclusion, our three solutions to this cubic polynomial would be, we have a real root at negative 3, we have one imaginary, negative 1 plus I, and we have our third, negative 1 minus I. Hopefully this has been of help. Thank you for your support of HansenMath.com videos, and I hope everyone has a wonderful day.